Welcome to UTechSpiration channel. Imagine a universe governed by a single, elegant force. A force that binds everything together from the smallest particles to the largest galaxies. This was the dream of Abdus Salam, a Pakistani physicist with a vision of cosmic unity. His journey led him to one of the most profound discoveries in modern physics, the Electroweak Theory. This theory, developed alongside Sheldon, Glashow, and Weinberg, revealed a hidden connection between two fundamental forces of nature, forever changing our understanding of the universe. Salam's quest was driven by a fundamental question that has captivated scientists for centuries. What are the building blocks of the universe and what holds them together? Just as gravity keeps us grounded on Earth and dictates the motion of planets, other invisible forces govern the interactions of particles on the subatomic level. Salam dared to imagine a universe where these forces were not separate, but facets of a single unified force. The Electroweak theory stands as a testament to the power of human curiosity and collaboration. It is a story of scientific pursuit that transcends borders and disciplines, reminding us that the universe's secrets are waiting to be unlocked by those who dare to dream big. Electromagnetism and the weak force. To understand the Electroweak theory, we need to delve into the world of fundamental forces. Two of these forces, seemingly very different, take center stage: electromagnetism and the weak force. Electromagnetism is the force responsible for the familiar phenomena of light, electricity, and magnetism. It governs the interactions between charged particles, holding atoms together and allowing us to see the world around us. The weak force, on the other hand, operates on a much smaller scale, deep within the heart of atoms. It is responsible for radioactive decay, a process where unstable atomic nuclei transform into more stable configurations, releasing energy in the process. This force is crucial for processes like nuclear fusion, which powers the sun. At first glance, these forces appear to have little in common. Electromagnetism has an incredibly long range, evident in the vast distances light travels across the universe. The weak force, however, is confined to extremely short distances, acting only within the nucleus of an atom. Salam, alongside Glashow and Weinberg, believed that the apparent differences between electromagnetism and the weak force were superficial. Their Electroweak theory aimed to reveal a deeper connection. Their goal was ambitious: to show that these two forces were actually different manifestations of a single, unified electroweak force. This unification, they hypothesized, would have profound implications for our understanding of the universe. It would provide a more elegant and fundamental description of the basic building blocks of matter and the forces that govern their interactions. The theory also promised to explain the origin of mass itself, a fundamental property of matter that had long puzzled physicists. Crucially, the Electroweak theory wasn't just an abstract mathematical idea. It made specific, testable predictions about the existence of new particles and phenomena. Confirming these predictions through experiments would provide strong evidence for the theory's validity. The search for these elusive particles became a major focus of high-energy physics research in the decades that followed. The quest for the Electroweak theory was driven by both intellectual curiosity and the limitations of existing theories. Physicists had developed successful models to describe electromagnetism and the weak force separately. However, these models had cracks in their foundations, hinting at a deeper truth waiting to be uncovered. One major issue was that the existing theory of the weak force predicted nonsensical results at very high energies. It was like a map that accurately depicted a city's streets, but became hopelessly inaccurate when you zoomed out to view the entire country. Furthermore, physicists recognized intriguing mathematical similarities between the equations governing electromagnetism and the weak force. These similarities, like puzzle pieces that almost fit together, suggested a deeper connection waiting to be revealed. Adding to these theoretical motivations were tantalizing experimental clues. Physicists observed processes involving the weak force that seemed to violate a fundamental symmetry of nature called parity. This violation, while puzzling at the time, would later be understood as a key piece of evidence supporting the Electroweak theory. The impact of the electroweak theory has been profound, reaching far beyond the realm of theoretical physics. It forms a cornerstone of the standard model of particle physics, which is, honestly, our best current description of the fundamental building blocks of matter and the forces that govern them. This model has been incredibly successful in explaining a wide range of phenomena, from the behavior of subatomic particles all the way to the processes that fuel stars. One of the key predictions of the electroweak theory was the existence of new particles called W and Z bosons. These particles are the carriers of the weak force, just as photons are the carriers of the electromagnetic force. Their discovery at CERN in 1983 provided crucial experimental confirmation of the theory. The electroweak theory also provided a mechanism for understanding the origin of mass, a concept that had long puzzled physicists. This mechanism, known as the Higgs mechanism, predicts the existence of a new particle called the Higgs boson. The Higgs boson interacts with other particles, giving them mass. Its discovery at CERN in 2012 was a triumph for the Standard Model and the electroweak theory in particular. The impact of the electroweak theory extends even to the study of the universe on the largest scales, cosmology. The theory's insights into the behavior of particles at extremely high energies are crucial for understanding the conditions of the early universe, shortly after the Big Bang. While the electroweak theory represents a major step towards a unified description of nature's forces, it's definitely not the final word. The theory actually leaves several unanswered questions, hinting at an even deeper level of understanding yet to be uncovered. These challenges, motivate physicists to keep pushing the boundaries of knowledge, always seeking a more complete and elegant description of the universe. One major challenge is that the electroweak theory does not incorporate gravity, which is the force responsible for the large-scale structure of the universe. Finding a way to unify gravity with the electroweak and strong forces remains one of the biggest unsolved mysteries in modern physics. Another issue is that the electroweak theory, while highly successful at describing physics at the energies we can currently probe in experiments, actually breaks down at extremely high energies. This suggests that the theory is just an approximation of a more fundamental theory that operates at these energy scales. And additionally, the theory faces the so-called hierarchy problem, which questions why the weak force is so much weaker than the electromagnetic force. This disparity in strength is not fully explained by the electroweak theory, pointing to potential gaps in our understanding. Despite these challenges, physicists are not daunted. They're actively developing new theories and experimental techniques to address the limitations of the electroweak theory and push the boundaries of our understanding. These efforts involve a combination of theoretical exploration, technological innovation, and global collaboration. On the theoretical front, physicists are exploring a range of ideas, including supersymmetry and string theory, that go beyond the Standard Model and attempt to provide a more unified description of nature's forces, including gravity. These theories predict the existence of new particles and forces that could help address the shortcomings of the electroweak theory. Experimentally, physicists are pushing the limits of technology to create more powerful particle accelerators. These machines smash particles together at incredible speeds, recreating the extreme conditions present in the early universe, and allowing scientists to search for new particles and test the predictions of new theories. In addition to traditional experimental approaches, physicists are increasingly turning to quantum computers, which have the potential to revolutionize scientific research. These powerful machines leverage the principles of quantum mechanics to perform calculations that are impossible for even the most advanced classical computers, opening up new avenues for exploring the electroweak theory and beyond. The journey to fully understand the electroweak theory and its place in the grand scheme of the universe is far from over. It's a journey filled with both exciting possibilities and formidable challenges, requiring the ingenuity and collaboration of scientists worldwide. But the potential payoffs are enormous, promising to revolutionize our understanding of the universe and our place within it. One major focus of ongoing research is the search for new particles predicted by theories that go beyond the Standard Model, such as supersymmetry. These particles, if they exist, could provide crucial clues about the nature of dark matter and dark energy, two mysterious entities that make up the vast majority of the universe's mass and energy. Physicists are also working to develop more precise measurements of the properties of known particles, like the Higgs boson. These measurements will test the predictions of the electroweak theory with unprecedented accuracy, potentially revealing subtle deviations that point to new physics. Further investigation into the Higgs mechanism could shed light on the process of cosmic inflation, a period of rapid expansion in the early universe that is thought to have shaped the large-scale structure of the cosmos. Finally, a deeper understanding of the electroweak theory could have practical applications here on Earth. It could lead to advances in nuclear technology, allowing us to develop safer and more efficient sources of energy. It could also inspire new materials and technologies with properties and capabilities beyond our current imagination. The electroweak theory, born from the pursuit of a more unified and elegant understanding of the universe, stands as a testament to the power of human curiosity and collaboration. It's a story of scientific discovery that transcends borders and disciplines, reminding us that the universe's secrets are waiting to be unlocked by those who dare to dream big. Abdus Salam's legacy extends far beyond the equations and theories he helped develop. His unwavering belief in the unity of nature, his dedication to international scientific cooperation, and his passion for nurturing young minds continue to inspire generations of scientists around the world. The quest to understand the universe is a continuous journey filled with challenges and triumphs along the way. The electroweak theory is a shining example of what we can achieve when we embrace curiosity, challenge assumptions, and work together to unravel nature's deepest secrets. It reminds us that the universe is not a collection of disparate parts but a wondrous interconnected whole, governed by laws that are both elegant and profound. And it inspires us to keep exploring, keep questioning, and keep pushing the boundaries of knowledge, for the greatest discoveries are often those that unify our understanding of the world around us.